Welcome to the Earth Science Classroom. You are looking at the East versus West subduction video in plate tectonics. This video is all about explaining the differences between the two types of subduction zones. So there's an East versus West. And looking at the differences, looking at the features, and of course giving you examples of where they are on the planet and the corresponding outcomes from each type. So guys, come join us for this video. Okay, so most of the subduction zones on our planet come with obviously convergent plate boundaries. And they are linked with active plate margins, with subduction, with flux melting, decompression melting, looking at the different slab velocities and how fast they descend, an underthrust underneath the kind of like lighter, less dense plate. So we can discuss obviously ocean to ocean convergence, ocean to continental convergence, and with subduction we don't really include continent to continent. That's more of orogenic formations, which we'll get to in a different video. But I've discussed both these plate boundaries in different videos. Want to check them out. And this one is basically just looking at the subduction zones and the differences between the two types. So there's two types, basically. There is the Mariana. Okay. And there is the Chilean or Chilean. Now, in terms of West versus East, the Mariana is going to be the West type, and the Chilean or Chilean is going to be the East type. Okay, so if we're looking at the Pacific Ocean, which is right here in this lovely drawn map, we can also discuss the plate as well, which is our basaltic composition, and this is the ocean plate that has the oldest ocean crust, so around 180 million years old. Now again, this differs a lot from the crust that is continental, that could be in the billions of years, these ancient cratons that don't really change much over time. They can be in the billions of years. But the ocean plates, they are produced or made at the mid-ocean ridges or rises. In this case, the Pacific Ocean is made through this kind of area right here. The East Pacific Rise goes around here underneath New Zealand and Australia, under the Indo-Australian plates, and you have like the Cocos plate right here, and the Caribbean plate. Then you have the Nazca plate right here, and the Chilean ridge. But you have this spreading center over here on the eastern side of the Pacific, and obviously this plate moves a great distance over a long period of time and is going to eventually subduct around this area. So there's subduction on both sides of the Pacific around the Ring of Fire, which is linked to both the earthquakes and the volcanism. So around here is our convergence. Okay, and there's some obviously around here in Indonesia and Malaysia. We have some up here with the Himalayas, but that's continent hitting continent. And over here in the Philippines, we have some through here. And then you got the Philippine plate here, that outlines the Philippine plate. Then through Japan. Japan's in that kind of meeting place of four major plates: Pacific, North American, Eurasian, and the Philippine. And up through here, all right, through the Russian peninsula there. You also have some through the Aleutian Arc right here. And then down through a little bit there in the Cascades or Northern Rockies and the Alaskan range as well. Kind of breaks for the San Andreas Fault Line in California, then comes down. And we have some right here through Central America, down through South America, through the Andes, and we have all this convergence. So we can divide this. If we have a line, we have the East this way of the line, okay? And so if we look at longitude, maybe it's the international date line, maybe, all right? So 180 degrees. And then obviously this way would be the West, So there's differences between the eastern subduction zones, which are called the Chilean. Obviously down here is Chile. And obviously the west, which is the classified as the Mariana type, which is over here. And the trench is like right here, Challenger deep, over 35,000 feet deep. And we have our lovely difference around the Ring of Fire based on the Pacific Ocean plate, because you have both, the majority is ocean to continental subduction convergence, and you have some ocean to ocean, like here with the Philippine plate and the Indo-Australian plate. You have some ocean to ocean. And we'll explain the differences in terms of the subduction zones now. So before I get into the different types in terms of the characteristics, I want to talk about the dip angle. Okay, so let's say we have this basic subduction picture. All right, here's my ocean crust, and it's going to subduct, and we have this other crust here which will not subduct, and it's right there. So let's just say this is ocean, so let's put a little ocean there, and this is continental. Okay, so we have our classic ocean continental convergence, and we have our subducting slab right here. We have our trench, we have our metamorphism of the sedimentary rocks and basalt, we have our different grades, we have our flux melting at certain temperatures, we have our maybe a diapir, which is the breaking through, maybe there's a spreading center here, but you have this general diagram showing the convection currents in the asthenosphere and the thickness, and there. Okay, and the mantle wedge right here, accretional wedge, all that good stuff. But what we care about is the dip angle. This angle at which the slab is descending or subsiding or being forced under or under-thrusting. The angle is very important. Now, what controls the angle? Well, research has shown that the velocity of the plate can dictate the angle and how fast, obviously, that slab is descending. The age of the ocean floor, the ocean crust, the older is going to be thicker and denser than, let's say, a younger plate closer to the ridge that's hotter. It's going to be colder slab, which again would change the dynamics of when that cold slab descends into the asthenosphere and down into the perhaps the asthenosphere mesosphere boundary at about 660 kilometers, which is usually the boundary of these slabs where they go, but there is research that shows it goes down to the core mantle boundary as well, and kind of like has this remnant of an old slab just kind of like sitting there and dictates a lot of the flow within both the mesosphere and the asthenosphere. And obviously the density, which is linked to both the age and composition. So the angle can change. The angle can be as much as around 80 degrees down to as maybe 10 degrees. And that would change. So let's just draw quickly a 10 degree. It's very, very shallow. Very shallow. This is like 10 degrees there. Very shallow. And you can see that there's a distinct difference in just the diagram and also what you'd think would happen in this situation. Or if we had a very extreme dip, okay, let me just make some room here. All right. So this would be like more of so this would be like, extreme dip of, 70 to 80 degrees, the angle. So the angle obviously is controlled by various attributes within the crust, lithosphere, and asthenosphere. And then once that dip occurs and you have this subducting slab at a certain angle, then you're going to have different features created when they converge. And we'll get onto that now. So the dip angle is very important, and there's a difference between the east and west in their dip angles. So the first type we're going to look at in more detail is the east type subduction, the Chilean type. Now, the dip angle, the average dip angle of the Chilean, so basically majority of convergent plate boundary and subduction that is on the eastern side of the Pacific Ocean, is going to be around 27-degree dip angle. So it's very shallow. It's a very shallow and not deep. So this would only really reach between 150 to 200 kilometers down, and the angle would be very shallow. This would cause certain things. So you'd have your deeper earthquakes, your Beanoff zone, being around 200 kilometers, all right, for the deep zone earthquakes that occur both. Now, the earthquakes, you're going to have more what's called megathrust. Based on the angle and the friction and the connection between the two plates, you're going to have more megathrust earthquakes and generally larger earthquakes, generally. And the earthquakes will occur in the above plate. Now, why? You also have a lot of compression. If it's a shallow subduction zone, it's going to be pushing more directly, more lateral pushing against that plate. So you would have some orogens or orogenic formation where the plates would create some folds, create some more metamorphism within the lower crust. You would have a higher, more extreme relief or terrain, a higher terrain, and you'd have less back arc development or marginal sea development. So you'd have less of that. So you don't really see many islands off the coast of both South America and North America because of the angle. There's not much room to develop a fore-arc or back-arc basin because it's being pushed together too much, and there's compressional stress applied to this subduction zone at the surface. So you get also some more violent volcanism, as your flux melting is generally going to be closer and a wider, broader range of volcanism based on the dip angle and where the subduction slab is. And it looks like this. So you have more compressional stress pushing in here. You've got the elevation change, obviously, with the compressional stress. You have some obviously very large accretional wedge and prism volcanism. Both the flux melting and decompression melting is here on the FM and DM, and the Beanoff zone is right here with the average dip angle. And what you also have to consider is the age. Now, why is this doing this? Why is it only a shallow, not very deep subduction zone? Is the age. So this, generally on the eastern side of the Pacific, is very young or younger, and it's usually hotter and it's less dense. Now, obviously, there's still a difference in density based on isostasy, so you have subduction, but it's not as a apparent difference in subduction. So you have the mid-ocean ridge being closer, with the East Pacific rise being right there, the Chilean ridge, you're really close. So this brand new oceanic crust hasn't had time to thicken or cool down before it starts to subduct under both North America and South America, both continental plates. So that's probably one of the reasons why. Could also argue there's convection current differences there, and velocity and composition, but generally it's the age that is causing this to occur. So now we're on to the west type subduction, the Mariana type, okay, Western Pacific. So interaction with the Indo-Australian plate, the Philippine plate, the Eurasian plate, and again the North American plate up towards the north, towards Japan and Russia, and also the Aleutian plate, the Aleutian arc. So what we have here is the dip angle is obviously the most obvious difference between them. So it's around 65 degrees. So this slab, this descending slab, is really descending really fast and really deep. So it's really deep, and it's around 65 degrees, the angle. So there is a further subduction of this slab down to depths of 410 to 660 kilometers in the asthenosphere, which is the area of transitional zone. Okay, before it gets to the mesosphere, there's also, which is the lower mantle, there's also research showing evidence of these slabs going into the mesosphere and traveling down as far as the core mantle boundary, which is insane. Now, they suggest that would disrupt certain movements and plastic flow of the mantle, both lower and upper, but it's very hard to, with it being so deep, to get some clear picture on that. So with the slab being a increased dip angle, you have the convection currents being allowing and encouraging this slab to go down, but also you have this uprising right here, this diapar, which is going to come up, this plume of material, in this case magma, is going to come up and force its way through the crust and start to form what's called a back arc basin. The flow is to replace what's being moved to the right to connect with the subduction zone. We also have our trench. We have our forearc wedge or forearc accumulation. We have our forearc basin. So as you can see, the terrain and topography of this subduction zone is completely different. You have obviously your volcanism. Your volcanoes form here, roughly around 110 kilometers from the trench. Basically, because it takes time and certain distance, you have a lot deeper Beanoff zone, which is around 300 to 400 kilometers. They've also done research that shows that earthquakes can occur in the slab, more on the slab, as deep as 700 kilometers, which is insane. But then you get the area which is aseismic because it's too ductile. It gets too hot and rocks become too ductile to really form very substantial earthquakes. But you have this zone of shallow earthquakes, intermediate and deep in these types of subduction zones. But you have this array of basins and arcs and volcanism forming because there is less compression and you have more tensional stress right here applied by the uprising material, causing things. So you get some islands like Japan and the Philippines that are off the coast, and you get a marginal sea between them and the continent, which is happening with this because of the slab angle. Now, you also get less violent earthquakes, but you get deeper earthquakes as well from this type. You get less accretion right here because there's less compression, less scraping, so you get less accretion. So again, that adds to a more gentle relief of that floating, not subducting plate right there. So to conclude, the dip angle is the main difference, and dip angle is controlled by the age of the ocean floor, the thickness, the composition, density, and also the velocity of the slab and the ocean floor. So the main difference is the angle, and this is going to be creating different features. So difference in the plate that is pretty much not subducting. So you could either have the origins or the compression. For the east, you could have the different back arc and forearc basin development. In the west, you have the difference in volcanoes, magma composition. Also, you have a difference in the amount of earthquakes and size of earthquakes versus megathrust versus regular, and the difference in Beanoff zones as well, the deep earthquakes foci. So guys, hope you enjoyed this video, hope this helps, and check out more videos on tectonics and also other playlists in this channel. Thanks a lot.